Hello, so this is the second part of my summary of lecture 20, inverse Cramer's rule and volume. So in the first part, we already proved this first point, so let's have that written here. So we have the A inverse is 1 over determinant A times the C transpose. So let's discuss about the Cramer's rule. So Cramer's rule has this way of explicitly compute the x through the determinant. So we know that the x is the A inverse times B, but now we have the formula for the A inverse, so why not plug that in and B. Okay, so the way Cramer's rule works is, so let's identify each component of x. So remember, the x itself will be like x1, x2 to the xn. So let's see what happens in the first component of x1. Let me give a green color. Okay, so we know that this will be like some kind of ratio, because determinant of A is scalar, so this will be like some ratio. And what is this C transpose B? Okay, let me write that something else. Okay, so let me write also the second part. Something divided by the determinant of A. And let's see more in detail about this one. So again, so you see some cofactor matrix with the transpose. So C1, 1, 1, and the matrix transpose, so C2, 1, C3, 1, and this is C1, 2, C1, 3, and so on. And then you multiply by the B, right? So B is just a column vector, a single column vector, n times n, or something times n. So B1, B2, and so forth, so on and so forth. So take a look at that and see that, so this is actually a part of x1, x2, right? So I'm just gonna tuck them in here to help us see more clearly. So this is the x1 is this term times this term, x2 is the second row times the column, and so on and so forth. You get the idea. So whenever you multiply some set of covector here by some set of another number, this is basically the covector formula to get the determinant of something, right? And then another thing is that this C, this covector of C, comes from what? It comes from, don't forget this formula, so this comes from the original matrix, the A, the capital A, the matrix A. So we're actually computing some determinant of some matrix. So let's name them the determinant of matrix B1. And the same logic goes for the second row for x2 here. So second row times this column. So you will count also, you will compute some kind of determinant here, of course with a different set of covariance. So BC2 and B2, C22, and so forth. And you will have this some determinant of some matrix that I will call B2. So what are they actually? So the B1 and B2 is a matrix with a column of B with the rest of the component are coming from A. So in other words, let me rewrite that again. So B1 is the matrix of A with the first column replaced with B. So this is the B and this is the A. So some kind of like that, but this is not completely A. This is A from the second column to the end. Same thing for B2 is you replace the second column of B. The rest of them is the matrix A, just as it is. And why is it A? Because again, this is the covector that coming from A, so you must have that the number of A to compute the covector of them. So I hope that's clear right now. And actually that is it for the second point, the Cramer's rule. So this is called the Cramer's rule. So we have like a really solid equation here. Like, so we can do it in terms of the formula instead of just computing x from elimination and what we did in the earlier lessons. But there's one thing that I want to mention that Professor Strang also said in the lecture, that actually this takes a really long time. It's quite a not really efficient way to compute the x. You know, the x1, we need to compute the determinant of b, which we need to compute the covector, and then God who knows like how large the matrix is, and then we need to compute the determinant as well. This takes really long to compute, and MATLAB itself, it always do the elimination. At least that's what professor mentioned in the lecture. So that's it for Cramer's rule. Thank you.